Welcome to episode 24, Cloud Storage Classes and Cost Strategy, where we explore how selecting the right storage class aligns performance with price. In cloud environments, cost efficiency comes not just from using less data, but from storing it smartly. Google Cloud Storage provides several classes that balance access frequency, durability, and expense. Choosing the right one means understanding how often data will be read, how quickly it must be retrieved, and how long it must be retained. By matching workloads to the correct class and region, organizations can significantly lower costs while maintaining availability and compliance. This episode explains how to design a storage plan that respects both technical and financial realities, making every byte count in service of business value. Google Cloud offers four main storage classes: Standard, Nearline, Coldline, and Archive. Standard is built for frequently accessed data. Think websites, applications, or active analytics pipelines. Nearline suits data accessed less than once a month, such as infrequent reports or completed projects. Coldline targets long-term but occasionally needed data, like compliance records or backups retrieved a few times a year. Archive is the lowest cost class, optimized for data rarely accessed but required to remain available for years. Each class shares the same durability and security, but differs in access and retrieval costs. The art lies in knowing when to move data between them, ensuring availability without paying for speed you no longer need. Access patterns are the compass for class selection. By analyzing how often and how quickly data is used, organizations can predict which class fits best. For example, product images on an e-commerce site might need immediate access daily, while historical sales logs are seldom touched. Choosing Standard for the first and Nearline for the second keeps both performance and cost optimized. Misjudging patterns can either slow access or inflate bills unnecessarily. Tools like storage analytics and access logs reveal usage trends over time, guiding data placement. The goal is not to guess, but to measure, using evidence to keep each data set in its most economical home. Regional and multi-regional placement add another dimension to storage strategy. Regional storage keeps data in one geographic area, ideal for compute tasks that run nearby and need low latency. Multi-regional storage replicates data across multiple regions, providing higher availability for global access, but at a higher price. The choice depends on user distribution and regulatory needs. For instance, a media company serving viewers worldwide benefits from multi-regional speed, while a regional ELF provider may require data residency within national borders. Governance frameworks ensure these choices reflect both cost and compliance, turning placement into a thoughtful balance rather than a default setting. Lifecycle policies bring automation to cost management. They define rules for when data transitions between classes or when it should be deleted. For example, a policy might state that logs move from Standard to Nearline after 30 days and to Coldline after 6 months. This reduces manual intervention and prevents forgotten files from accumulating cost. Lifecycle policies enforce discipline silently in the background. They embody the principle that data value declines over time, and storage should reflect that decline. When applied carefully, lifecycle automation keeps storage efficient, predictable, and aligned with real business timelines. Retrieval costs, operation fees, and minimum storage durations are vital to understanding total expense. Lower-cost classes, such as Coldline and Archive, impose fees for access and early deletion to encourage long-term storage. These are not penalties, but signals. Each class rewards behavior it is designed for. For example, pulling archive data a day after upload incurs higher cost because the system expects it to rest for months or years. Operations like listing, copying, or deleting objects also carry small costs that add up at scale. Awareness of these details allows architects to forecast expenses accurately and prevent surprises on monthly bills. Egress costs, the charges for moving data out of the cloud, can dwarf storage costs if not managed wisely. Data leaving a region or the Google network incurs transfer fees that vary by destination and network path. Keeping compute close to storage minimizes egress, as does using caching or regional replication for nearby users. For example, a video processing job running in the same region as its raw footage avoids unnecessary transfer costs. Planning data movement as part of architecture rather than as an afterthought turns egress into a controllable variable. Thoughtful design keeps data local to where it's needed most. Object versioning and soft delete protect against accidental loss. Versioning keeps old copies of objects when new ones are uploaded, allowing recovery from unintended overwrites. Soft delete, enabled through retention policies or bucket settings, preserves deleted data for a defined period before permanent removal. These safeguards add resilience but can also increase costs if not monitored, since older versions remain billable. The key is balance. Retain what's necessary for compliance or rollback while pruning obsolete copies regularly. In practice, versioning serves as a safety net for human error, giving teams confidence that mistakes need not be catastrophic. Security in cloud storage relies on strong encryption and fine-grained access controls. Every object is encrypted at rest by default, and customers can add their own encryption keys for additional assurance. Identity and Access Management, or IAM, policies define who can view, edit, or delete objects. Access can even be managed per object rather than per bucket. For sensitive data, audit logs track every access attempt. Together, these controls ensure confidentiality without complicating operations. Security in storage is not just about preventing breaches, it is about maintaining trust in the data lifecycle from creation to archival. Performance tuning in cloud storage focuses on throughput, parallelism, and object naming. Uploading and downloading large files in parallel increases speed and efficiency. Naming conventions also affect performance. Evenly distributed object names avoid hotspots that slow access. For example, prefixing file names with timestamps rather than sequential numbers spreads load evenly across storage nodes. Applications reading or writing many small files benefit from bundling them into composite objects. These practical habits make performance predictable and consistent, ensuring that even large-scale operations complete efficiently without unplanned latency. Backup, archival, and compliance retention use cloud storage as a long-term foundation. Backups protect operational data from corruption or loss, while archival storage fulfills legal or regulatory mandates to preserve information. Coldline and archive classes suit these needs, combining durability with low cost. For instance, a financial firm may retain transaction logs for 7 years in archive storage to meet audit requirements. Retention policies enforce minimum hold periods automatically, ensuring compliance without manual tracking. In regulated industries, this automation reduces risk and simplifies oversight, proving that cost-effective storage can also meet the strictest governance standards. Monitoring usage and detecting anomalies are critical for maintaining control. Cloud monitoring and logging tools show how much data is stored, accessed, and transferred, revealing unexpected patterns. Sudden spikes in egress or operations might indicate misconfigured applications or unauthorized access. Setting alerts for these anomalies prevents cost overruns and strengthens security. For example, if a bucket suddenly triples in access frequency overnight, the team can investigate before costs escalate. Monitoring transforms storage from a passive service into an actively managed resource, ensuring efficiency, transparency, and safety. Cost optimization combines all these insights into a repeatable playbook. Start by classifying data according to access patterns, then apply lifecycle rules and monitoring to keep it aligned over time. Use cost calculators to model different storage and egress scenarios before implementation. Regularly review usage reports to identify forgotten datasets that could move to colder storage or be deleted. Optimization is an ongoing process, not a one-time exercise. As workloads evolve, so should storage strategies. When teams treat cost management as part of design rather than a late audit, savings emerge naturally through better choices. Designing for access economics means viewing storage as a spectrum, not a single tier. Each class serves a purpose, and the smartest strategies use them in harmony. Fast access has value, but so does low cost, and governance defines where each belongs. Cloud storage allows organizations to blend these priorities dynamically, adjusting as data ages or priorities shift. By aligning storage classes, lifecycle rules, and monitoring, you ensure that resources reflect actual usage, not assumptions. The result is a sustainable, transparent, and resilient data environment that pays for performance only when performance truly matters. Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.